Today we are going to focus on confidence intervals for population proportions. This video explains how proportion confidence intervals work from start to finish when using statistical software. The focus is on understanding what is being estimated, what information the software needs, and how to clearly explain the result in words. This video addresses one specific kind of question. We are estimating a proportion. A proportion is a percent of a population that falls into a particular category. Another way to think about a proportion is this. Out of every 100 individuals in the population, about how many fall into the yes group? Proportions can be written as percents, like 55%, or as decimals, like 0.55. These are just different ways of expressing the same idea. A population is the entire group you want to describe. This might be all students at a college, all customers of a company, all voters in a city, or all items in a shipment. The population is the group you are ultimately trying to learn about. A sample is the smaller group you actually collect data from. The sample is used because measuring everyone in the population is usually not practical. The goal is for the sample to represent the population as well as possible. A proportion always comes from a yes or no question. Each individual or item either belongs in the yes category or the no category. There are no partial answers. This is what makes a proportion different from an average or a measurement. Examples of proportion questions include the proportion of students who pass an exam, the proportion of customers who would recommend a product, the proportion of voters who support a candidate, or the proportion of items in a shipment that are defective. In each case, every observation can be sorted into one of two groups. Software and textbooks often use the word success. In statistics, success does not mean something positive happened. Success simply means the category labeled yes. If the question is about defective items, defective is still considered a success because it is the yes category. The word success is just a label, not a value judgment. The population proportion is a real number that describes the entire population, but it is usually unknown. That is why a sample is taken. From the sample, we calculate a sample proportion. The sample proportion is found by dividing the number of yes responses by the total number of observations in the sample. This value is our best single estimate of the population proportion. Different samples would usually give slightly different sample proportions. A confidence interval accounts for that natural variation by giving a range of reasonable values for the true population proportion, instead of only one number. A confidence interval is always tied to a confidence level. Common confidence levels include 90%, 95%, and 99%. The confidence level describes how the method performs when it is used repeatedly. If the same sampling process were repeated many times and a 95% confidence interval were created each time, about 95% of those intervals would contain the true population proportion. The confidence level does not describe the probability that the true proportion is inside one specific interval. The population proportion is fixed. It does not change. What changes from sample to sample is the interval. Some intervals will contain the true value, and some will not. That behavior is built into the method. A common incorrect statement is that there is a 95% chance the true proportion is in this interval. The correct interpretation is that the method used to create the interval captures the true proportion about 95% of the time, when it is repeated across many samples. Every confidence interval follows the same basic structure. It is an estimate plus or minus a margin of error. For proportions, the estimate is the sample proportion. The margin of error is the amount added to and subtracted from the estimate to form the interval. When software reports a confidence interval, it usually shows two values. The smaller value is the lower bound, and the larger value is the upper bound. The estimate is centered between these two values. The distance from the estimate to either bound is the margin of error. The margin of error is the same amount on both sides of the estimate. For example, if a confidence interval goes from 48% to 62%, the midpoint is 55%. That midpoint is the estimate. The distance from 55% to either end is 7 percentage points. This can be written as 55% plus or minus 7%. The total width of the interval is 14 percentage points, but the margin of error is half of that width. The margin of error describes precision. A smaller margin of error means the estimate is more precise. A larger margin of error means there is more uncertainty about the true population proportion. 3 factors affect the margin of error for a proportion. Higher confidence levels produce larger margins of error, because the method must capture the true value more often. Larger sample sizes produce smaller margins of error, because more data reduces random variation. Proportions closer to 50% tend to have more variability, which leads to larger margins of error than proportions closer to 0% or 100% when sample size is the same. Before using software, several pieces of information should be identified. The first step is confirming that the question is a yes or no situation. The second step is clearly defining what counts as yes. The third step is counting how many yes responses are in the sample. Software may call this value successes, X count, or number of successes. All of these terms refer to the same idea. The fourth step is identifying the total sample size, often labeled as N. The fifth step is choosing a confidence level. Once these values are known, the software can be used effectively. Consider the following example. The goal is to estimate the proportion of students at a college who have taken at least one online course. The yes category is students who have taken at least one online course. A random sample of 200 students is collected, and 110 of them say yes. At this point, the number of yes responses is 110, the sample size is 200, and the confidence level is 95%. In the software, the option for a one-sample confidence interval for a proportion is selected. The number of successes is entered as 110. The sample size is entered as 200. The confidence level is entered as 95%. The software produces a confidence interval. Suppose the output is 0.48 to 0.62. These numbers are proportions written as decimals. To express them as percents, they are multiplied by 100. 0.48 becomes 48%, and 0.62 becomes 62%. The interpretation is stated as follows. At the 95% confidence level, the true proportion of all students at this college who have taken at least one online course is estimated to be between 48% and 62%. The margin of error can also be stated. The estimate is about 55%, and the interval extends about 7 percentage points in each direction. This is the same idea used in opinion polls when results are reported as a percent plus or minus a margin of error. Changing the confidence level would change the width of the interval. A higher confidence level would produce a wider interval. Increasing the sample size would produce a narrower interval because the estimate would vary less from sample to sample. A second example reinforces these ideas. Suppose the goal is to estimate the proportion of phones in a shipment that are defective. In this case, yes means defective. A sample of 200 phones is inspected, and 10 are found to be defective. The number of yes responses is 10, the sample size is 200, and the confidence level is 95%. These values are entered into the software. Suppose the resulting confidence interval is 0.02 to 0.08. Converting these values to percents gives an interval from 2% to 8%. The interpretation is stated as follows. At the 95% confidence level, the true proportion of defective phones in the shipment is estimated to be between 2% and 8%. This interval is narrower than the earlier example, even though the sample size is the same. That result is consistent with the fact that proportions far from 50% tend to have less variability. Confidence intervals for proportions rely on samples that reasonably represent the population. Random sampling is ideal. Confidence intervals describe random sampling error and do not correct for bias. For example, surveying only students in one class would not represent all students at a college, even though the software would still produce an interval. The method also works best when there are enough yes and no responses. If the sample is very small or nearly all responses fall into one category, The interval may not be reliable even though the software produces a result. When working with confidence intervals for population proportions, a consistent process is useful. Confirm the situation is yes or no. Define the yes category. Count the yes responses. Identify the sample size. Choose a confidence level. Enter the values into the software. Read the interval. Convert decimals to percents if necessary. Write a complete interpretation in words. Confidence intervals for proportions provide a way to estimate a population percent while accounting for uncertainty. The calculations are handled by the software, and the interpretation connects the numerical result back to the real situation being studied.